at this. Oh, come on. Okay. All right, so the last time we stopped, we have been talking about the algorithm analysis, and today we're going to continue on that topic. And I've mentioned an example that actually, like, no, I wouldn't say that I flew through or I just worked through really quickly, but I'm actually like, I want to work through it again with you guys, just to remind you what we are working with. But before that, before revising that example, because I'm gonna actually write, like, I'm gonna look at it in code in C#, and then we're gonna step through it, so we can confirm what I'm saying, and then we're gonna analyze it again on paper, like on the board, and then we carry on with the subject, like we carry on with other examples. Okay. Now there are a couple of things. When it comes to algorithm analysis, which I haven't mentioned the last time because I wanted actually to go into examples first, but then time to mention a little bit of the dry side of the subject. We have two types of analysis actually. I'm not talking about the notations of functions. I'm talking about the analysis itself. So we have, let me actually write this down. So types of this. You have priori analysis. I have posteriori analysis. Oh. Okay. Well, the priori analysis is we don't care about the code itself, right? So let me just, like, I think it's quite far. Again. So we all about code. Nobody talks about anything regarding that part. Just we talk about the algorithm. Like when we of all numbers in an array last time, we did that sum, and we actually looked at it from pseudocode. Well, yeah, because the pseudocode was actually, because the code was simple. I mean, it can be translated directly to a programming language, but in some complicated algorithms, more complicated algorithms, you will see that there are some stuff which are not really straightforward translatable into a syntactical code. You need to add more code in order to implement, let's say, one-liner or two-liners of the algorithm. So in the primary analysis, we care about the algorithm. We are completely independent from language. What programming language do you use? All right, we don't care about that. And it's independent of hardware. Independent from hardware. Okay. So and this is also important because in the priori analysis, we just simply again analyze the algorithm regardless of where it will run. So whether it will run on a phone, or whether it will run on a microcontroller, or it will run on a server or a quantum computer. We just simply like analyze the algorithms, like in the priori analysis, we analyze them independent from that. And we usually analyze time and space functions. Time and space functions. Okay. Like in the last time when we mentioned like how we measure a speed of an execution, we say a certain line of code took a single unit of time to execute, right? We don't care how many megahertz or how many seconds or how many seconds or minutes. We just simply say it took one single unit of time. Posterior analysis, however, right now, you are actually analyzing the program itself. Right now, the actual code, the actual text which you have written, the compilable code, this is the one which we analyze. This is what we call the posterior analysis. The other thing which we also look at is also language dependent, because there are some languages which actually help some algorithms to run. Like you can write better algorithms with than the others. So for example, writing an algorithm for a quantum computer definitely is going to be different from writing an algorithm for a classical computer, which we are having right now. Okay, so how do you write the program? How's the language? What is going to be the language used to implement that program or to implement that algorithm? It's also, when we are actually doing the analysis, it's going to be also hardware dependent. Okay, and when we measure time in whatever milliseconds, microseconds, nanoseconds, whatever, and we measure the space in bytes or qubits or whatever, right? So in terms of space, right? So this is these are like the two types of analysis that you're gonna that actually that we can commonly say they exist when it comes to software engineering or in algorithms analysis. You usually like encounter these guys, either this or that, when you are working with something, when you are working on a project. So usually what we do is sometimes a problem, like we have a problem and we think about the problem. Like I would like to sort all the people older than 60, giving them by their pension, for example, by their how much pension they are getting, descending or ascending, let's say. And then you say, okay, I'm gonna actually use, I don't know, like you can write there, I'm gonna sort them using, I don't know, quicksort or insertion sort, and then I'm going to give them arrays based on a certain other algorithm which will execute, and then you can start analyzing these steps on paper. And you don't actually think about where this will execute. You are just simply analyzing what you're actually gonna do, and this what you actually do is practically the priori analysis. Once you actually start implementing the code and you start to trying to make it faster, analyzing the problems and the runtime issues which you get, like how long it takes to execute a certain piece of code, or how big of a space does it take in which, I don't know, 1 million people, let's say, in memory, and so on and so forth. This is right now your posterior analysis is going to happen. So these stuff are actually happening in real life, just we name them, practically speaking. Okay. So that's the stuff which I wanted to mention before we dive in deep with the examples. So we keep that in mind. Okay, so let's get back to our space example. Some example. Sorry. Let me actually just double check if nothing in the chat, which is okay. I'm gonna actually write down the sum function again, which we had last time, and let's analyze it one more. So sum, if I have an array of numbers, array A, and n, which is the size of the array, and this is like old style C, let's say. A variable s, and then, well, actually, I'm gonna, yeah, I have this habit of semicolon, even though there's no need to, but okay, because this is a pseudocode at the end. And then for I equals to 0, I is less than n, and I plus plus, and then s equals to s plus a of I. We close, and then we return s, and we close the braces. Okay. So the space analysis, when we did it, so actually analysis, we had allocated, so we needed to allocate a, which size of n. We had to allocate s, which is a size of one unit, one memory unit, whatever it's going to be. Okay. And a is the array which I would like to sum. So if it's an array of integers, then it's going to be an array, let's say, where n is equal to 10, let's say. So 10 is 10 integers array. Now we need 1 because it stores only a number, which is how big of an array this thing is. We also need to allocate I, which equal also to 1, which is just simply a variable holds the number, which I can increment and keep track of where I actually at in the loop. Okay, so this is the stuff which we had, and we concluded that the space equals to s of n equals to n plus 3. So the space is the function of a space, or the space complexity of this program is just n plus 3, which we usually say is going to have a degree or an order O of n. Okay, and we're going to talk about this in a minute, why it is O of n. But let's actually talk about time right now, which is very important to get. Okay. So the time complexity, as I already have mentioned before, this guy takes one time unit to execute, right? And if you remember from the last time, a program is usually being broken into multiple pieces. Like a single line can be broken into multiple pieces, right? And then when I ask you guys, well, actually, let me ask you again as well. Do you remember how many times this will run? And feel free to directly or wherever.
4n plus 3.
4n plus 3?
3n plus 4.
N minus 1.
N minus 1. No. How okay, hang on. How many times this will run? Only this piece.
Once.
Only once. Okay. And this will run?
N times, checking it every time.
N plus 1.
Yeah, you see this, it should be n plus 1, and I will actually prove it in a minute. N plus 1. What about this?
N.
That N.
N. Okay. Line a little bit shorter here. So this is n is going to be 2n plus 2. 2 plus 2. This one is actually okay. How many times this will run? Anybody in the chat?
No, but I know
No
it's just
one?
me, but it's lagging for me.
Oh, hang on. Come again, please. Sorry, I cannot hear you.
I don't know if it's just me, but it's lagging for me. I don't know if it's my internet connection.
I don't know. You have to tell me. Everybody else, is it lagging for you also?
It is also
Yes.
lagging for me.
Okay. I don't know how to help you here, but
It's fine now, but through certain periods it's lagging.
okay. In case if I'm lagging again, please tell me to repeat. I see that my Wi-Fi network is just jumping a little bit between two variables, apparently. So we'll see how I can try to improve here. Anyway, do you guys know like how long this will take?
N.
Well, it will take n. How long this will take?
1.
1. Okay. Now let's actually jump into Visual Studio here. I actually took the same program, identical to it. Now, obviously, this is not how you would write it in C#. I mean, there is much better way of writing this in C#. But I've actually I just copy pasted the exact syntax so we can actually see it together. So I'm actually gonna see if I can with the pen put a breakpoint. Okay. Oh, now you give me a keyboard, do you? Okay. So I'm actually gonna start here. Oh, sorry. I'm gonna just put it right there, to be honest. Oh, where did I put the thing? There we go. So I'm gonna actually start. I want it to be exactly on the for loop. And right now, I'm calling this. So I'm having here 5 ones, right? And I'm giving a length of 5. Okay. This is why we are having this little guy, this I less than n. This is why we're having it n plus 1. If you haven't I know this is going back to the programming 101 or introduction to programming, but it's good to get solid foundations first before we run, right? So I'm gonna let's see, step over F10. So this is executed only once, right? So this is gonna be executed once. This is executed right now. So this is 1. And then it immediately jumps inside. This guy hasn't executed yet. The I++ never executed yet. So I less than n has executed at least 1 beside the I++. And you're going to see right now, so if this is 1, and this is 1, and this is 0, okay? So we actually run this, move on. And then right now, this runs for the first time. Then this runs for the second time. So there's 1, 2, 1. And then we increment. And this is right now 2, 3. And then we go on. And so on and so forth. Oh, all right. I was happy triggering stuff. So at the end of the day, that thing actually run n plus 1 times, just to confirm that. So let me actually close this before it actually like close all windows. There we go. So this is like me stepping through the code just to confirm that this is the actual thing running is that in that way. Now, when we actually like look at calculating the complexity of this function, we're gonna say that, okay, this is gonna be in total of I think 3n plus 4, as one of your colleagues said, so 3n plus 4. Yeah. So this is the function of time. So let's say if this is s of n, or this is going to be t of n, or f of n is going to equal to that. And now the problem here is when we give an estimate of how long this function runs, we usually say all the constants are not important, and we grab the variable with the highest polynomial order. Now, a polynomial is, for example, x squared plus c equals, let's say, 0, for instance. Well, it's actually like, I think it's not exactly this one, but hang on, let me double check. I have actually written somewhere like a collection of them. So let me actually like write this down in a little bit different way. So here's a side note. Let me actually put it right there. And I'll write it in white. So a side note, 3x squared. This is called monomial. Okay. This is weird. Hang on. Uh, 3x squared minus 4x. This is called binomial. Um, 3x squared minus 4x plus 5 is going to be called trinomial. And then when you have 4x squared, or 4x, let's say, cubed, minus 2x squared plus x minus 2, this is going to be polynomial. And if you remember from high school, when we say what is the polynomial order of a function, which looks like this or like this, you would say which variable having the highest exponent, or having the highest, like this is called an exponent. Okay, so the variable with the highest exponent in our case is, let's say, these guys, right? So in here, this is a polynomial, let's say. We call it generally, we generalize them under a polynomial. And when we say what is the polynomial order of this function, you say, for example, let's say for this guy is going to be x cubed. This is the polynomial order of that function. For this function is going to be x squared. For this function is going to be x squared. For this function is going to be x squared. For this function is going to be n. And when we say a polynomial order, we say order. So we write O of n, denoting it's a polynomial order. Does this make any sense?
Yes, yes.
Okay. So I just wanted to make this clear, because people, when they look at this O, they say big O. And this is not big O. This is actually the polynomial order of the function. Okay. let's actually dive in a little bit more. Let's actually talk about, for example, let's take another example. So we'll just go down here. I'm gonna have, let's say, adding 2 square matrices. So another example, adding, just a little bit. Oh. Two square matrices. So if I have an add function, which takes a matrix A and a matrix B of size n, and because they are square matrices, it means that if I put here 4, right? If I say n equals to 4, right here, that means I have a 4 by 4 matrix. Okay, so if I say n equals to 4, that means I have a 4 by 4 matrix. As simple as that. Okay, just to be clear. I'm going to actually sum them up. So I'm going to have a for loop for I equals to 0. I is less than n. I plus plus. And let's grab, because it's actually a nested for loop, for j equals to 0, j is less than n, also j plus plus. And as you can see here, I haven't defined even a result somewhere, but let's say I'm having a C of I and j, which is going to equal to A of I and j plus B of I and j, right? Closing the braces of these guys, closing the braces of these guys, and closing the braces of these guys, okay? This is a very simple program. And of course, you can say return C, right? C can be defined somewhere here if you want to. It's not an issue, right? But we actually don't care about this detail right now. What we care about is the actual analysis. How long will it take for this algorithm actually to run? What is the polynomial order of this function, right? So let's actually talk about time complexity. I'm going to actually ignore right now the space complexity. I'm going to really focus on time complexity from here on out. So approximately how long this will take? How many times will it run?
Two n plus 2.
Cannot hear you well. Sorry.
2n plus 2.
2n plus 3. Okay.
2.
2n plus 3. Okay, how about this? How about this? So based on what we have discussed last time, we can actually approximate things. Okay. So what you said actually is right. It's 2n plus 3, but we're going to approximate it. So we usually ignore constances, right? So at the end of the day, we can say, because we're approximating things, I can say that this runs for n times. Okay? Because of the constants, we just simply ignore them for now. Now here comes the interesting part. How long this will run? Any
Same as
wild guesses are fine.
The same as the I for loop.
Come again, please. Sorry.
The same as the last one.
Well, okay, the same as the last one, but we are missing one bit. This is a nested for loop, so it's not yet complete. So you got part of the question, like part of the answer. N squared, why?
Because every time the first for loop runs, it will run the second one, the nested one.
It will run the
Okay.
second nested loop for n amount of times, right? So that's the actual point of it. So for every time, for every single time this guy runs, this guy will run n times. And this is why we say n times n. Okay, so I repeat again, just to reiterate, every single time this guy runs, so every one tick, so this guy ticks once, this guy ticks n times. And this is why you need to multiply it. Okay. And if you don't believe me, just put a program similar to this, put in a breakpoint and count it. Okay. So the question comes here is, right now we're actually approximating it, of course. But the question comes here is, how many times this will run though?
N times n.
N times n again, exactly. Okay. So if we approximate all of this stuff, so this is n plus n squared, right? So this is like what? N plus n squared, which is going to be 2n squared plus n, right? Which we approximated to polynomial order of
N squared.
because we are grabbing the highest exponent. I'm really going slow here as much as I can. Is everybody is okay so far?
Yes.
Okay. If it doesn't make any sense, just scream. I'll try my best to explain again. Okay, so a nested for loop, basically speaking, gives you always an n squared, almost. In this, at least in this case, without an exit, without a specific exit condition. Please understand that I'm giving you like this is like some sort of a template programs. So in this case, this is easy to figure out. But if you had an if statement somewhere where it says break, because break exists as a keyword, right? You can break out of a loop by just calling break. Now you need to analyze it in a different way, which we're going to discuss in the future. But for the time being, this is the very straightforward way of analyzing. Just this is like a nested for loop, and this is like a single for loop. So a single for loop usually runs for an n time, for as long as that number exists, or that number haven't been reached. And a nested for loop is going to be, again, for the same thing. Okay. There's one more thing I would like to just highlight. I'm not going to discuss in depth, but I'm just going to highlight here just in case you guys might miss it. What happens with recursion? So another example, which is going to be factorial. Now, all of us, as we already know, that any recursion, almost any recursion, I think it should be all any recursion, can be extracted into a into a loop, right? Or can be expanded to a loop. So if I'm having a factorial function which takes n, well, let me write it in a small letter so I can make my life easier writing. So if n less than or equals to 1, we return 1. Else, we return n times factorial of n minus 1. Can somebody give me a guess how long this will run? Anyone? Come on, give me a wild guess.
Well, the whole function runs once, but it's gonna constantly repeat. So basically, n times or
Exactly. So it's O of n. The function will keep repeating until you run out of n, because n is being decreased, and you are checking here, and this is your exit condition. Sorry, this is your index condition, and you exit from here, right? So it's actually O of n. So recursions are usually interesting to analyze, maybe, but at the end of the day, they are similar to loops, but they are like maybe annoying a little bit to analyze, right? So that's one. That's one example regarding recursion, which I actually wanted to mention here. So let me actually double check. We are still on track. Let us actually talk about. Let's grab more examples. Let's have an array operation, a certain array operation which nobody cares about. It just does something. So I'm gonna write it here. Array operation. That's the name of the function, which takes an array of array and the size. Again, we are writing in the C style. And then we have a for loop. For I equals to 0, I is less than n, I plus plus. And here, I'm just simply saying I equals to 0. Then we move on. We have another for loop. We're going to call this I as well equals to 0. I is less than n, I plus plus. We open braces. One more for loop here. J equals to 0. J is less than n. J plus plus. And right now we have A of I plus equals A of I plus I plus J, which means nothing in our case, but it's just a piece of code that we would like to analyze. So this closes this closes that. And the final, this closes that. Okay. Now here comes the question. What is the time complexity of this function?
And again,
Not n, and somebody figured out as n squared. Can you please, in the chat, if you would like to write it in the chat, can you please state why it's n squared?
Can you hear me?
Yes, I do.
Other four loops, two other four loops are not connected to first one.
Mm-hmm.
So they are previously you worked on them. They are n squared.
Mm-hmm.
They are, because it's the highest
Exponent.
exponent, we take as the polynomial time.
Exactly. So this guy, to reiterate, and thank you very much. So this guy repeats for n squared. Oh, sorry, for n times, only n times. Okay, approximately again. And this guy repeats for n. This guy repeats for n times n, right? And this guy repeats also for n times n. Okay. When you sum things up, when you do the math, which I don't know, like what, n squared, 2n squared plus 2n. So 2n squared, hopefully I didn't miss anything, plus 2n, which we again always approximate to the highest exponent. So we say, okay, who has the highest exponent? This is going to be the polynomial order. So when we say what is the polynomial order of that function, we say the polynomial order of n squared. Okay. So don't get confused by the curveball of, for example, having a for loop like this. Okay. All right. So let's have more fun. Would you like actually to have a break before we carry on? So I can actually give you a break right now. It is actually 4:50. Let's actually meet at 5. So you have like 10 minutes break to breathe a little bit. And yeah, and if you have any questions, please write them in the chat and I will answer them.
Okay.
Hello?
Hello.
Okay, I thought that I lost the connection or something.
You are lagging. I mean, your voice is.
All right. Sorry about that. Probably I need to find a better, like I don't have any better reception area to be precise. Give me a second. I'll try to see if I can actually figure out a way to get a better reception. Okay, how about now? Better? Is it less lagging?
Yes, it's better.
Okay. All right. Okay, so let's carry on then with the next examples. So we talked about the this curved ball, which I've actually thrown at you for fun. And let's talk about what happens when you have a like similar one. So another similar example, just to get you warmed up for the upcoming ones. So let's say we have a function that multiplies, let's say two matrices or something like that, but you can do other things with it. But let's say multiply, I'm going to call it that way. And it takes well, I mean, it multiplies two matrices and it gives me a matrix set as an output A, B, and the size n of these matrices. And then we have A4, I equals to 0, I less than n, I plus plus, and then we open a brace, then we have another 4, j equals to 0, j less than n, j plus plus, and then we have a result, let's say C, which is going to have C of I and j equals to 0. And then we have another for loop. K equals to 0. Wow. K is less than N. And K plus plus, right? And then we have the C. We try to make it a little bit better. C of I and J, like so, equals to C of I and J. Let me close the bracket. Plus A of I K times, I don't know, B K of J, right? And then we close the braces. So this closer to this is going to be closer to this, and this is going to be closer to that. And this is the end of the function, right? And then you return the multiplication somewhere in the bottom, which we don't care about currently. But actually, let me pick up the yellow pen here. Can somebody give me a guess? Or not a guess. Right now we shouldn't be guessing. Right now we should be calculating. So can somebody tell me what's going to be the complexity of this guy?
N to the third.
N to the third. And here's why. This guy runs N times. And if you are, I'm actually analyzing it step by step because you need to learn how to unstuck yourself from exams in case you forget stuff. And this guy will run for N times from this guy's perspective, right? And this guy will run N in the first loop, right? And this guy will run N. And then when we get here, this guy will run again for N times, so times N. So this becomes an N squared. And this guy will run from the perspective of the red guy, is going to be also running for N times. And this guy from the perspective of the red loop is going to be also running for N times. Okay. Now let's actually grab another color, blue, fine by me. This guy will run for N times, right? And this guy will run for another N times, right? So if you sum things up, you're gonna actually get, I don't know, like right now, what, N plus 2N cubed or something like that. So, I mean, besides the other guys as well. So at the end of the day, you get a polynomial order of N cubed, right? Approximately. So this is the polynomial order, time of execution of this function. Does anybody can tell me like what is the space complexity of this guy? For fun?
Is it 10?
Actually, no, because this is a matrix. A space complexity. Do you remember? Like the matrix is
N squared.
N squared, exactly. So it's actually should be like, yeah, so that's what I meant. It's a square matrix for in our case. So the space complexity for this guy is gonna be N squared. Okay. You see how I analyze this? So I just simply said, like, from the perspective of this for loop, I just simply said how many times anybody inside will execute, right? And this also going to be N, and it's going to be also from the perspective of the red guy is going to be times N. Okay, just to be like consistent. So what I wanted to say here is I looked at it like if in case you get like 4 nested for loops or something like that, and you get lost for some reason or another, you just simply say, from the perspective of one loop, how many times whatever's inside is going to execute, and then you keep multiplying. So in this case, from this guy's perspective, this will run n, and then from this guy's perspective, this will run times whatever was before it, and times whatever was before it, and so on and so forth. Just to make your life a little bit easier in case you get stuck. But I think you can start recognizing some patterns here. So let's actually like have a look at this really quick before actually like right now we start to get used to the idea of nested for loops and stuff like that. So let me write down the patterns and then for these guys, and then we can actually step up the difficulty just a tiny little bit. Okay. So so whenever we have a for loop of I equals to 0 and I is less than n and I plus plus, and we usually don't care what code goes here. If there are no loops anymore, we just simply say that this takes an n, right? And then when we have if in case you guys had like for I equals to, let's say, n, and I is larger than 0, and I minus minus, and you got a code, a statement, a simple statement, which nobody cares still about because there are no infinite, like no nested loops or anything, you will also say that it's also executed for n. So we know these patterns, right? Now here's the interesting part. What happens if you have a for loop? I equals, let's say, to 1, and I is less than n, and then I plus equals 2. So you are jumping by 2's now, right? And the code goes here, okay? Now what's happening here is you are stepping by 2, right? You are jumping like 2 elements by 2 elements by 2 elements. So your function is in fact your function of n. If this is within a function that takes n elements, it will actually be n divided by 2, isn't it? And then when we ask what is the degree of this polynomial, we say it's actually degree of n, because it's the degree of the polynomial we are asking for, okay? Which is super important. Yes, indeed, you will not actually execute every single element in the array. You will not get every single element in the array, but we are approximating according to the polynomial order. And this is one of the things you're going to see later on that what we are doing, which is called asymptotic analysis. Asymptotic analysis isn't that very good. It just gives you a very crude way of telling how bad or how good a function is going to be. Usually, it's much better to use the amortized analysis, but the amortized analysis is like, I think it's going to be, I mean, it's right now for the current lecture it's way ahead, but it's not, we shouldn't talk about it right now, but generally speaking, it's more practical. But in any case, when you see something like this, you immediately know, well, quote unquote, something similar to this pattern, you know that's actually almost like O of n. It's not that big of a deal. It's not that very, very big of a difference. Okay, so if you have if you have a nested for loop, we already know that this pattern yields us a, hang on, I need to focus writing. Gives us a an n squared. So j equals to 0, j less than n, j plus plus, right? And then whatever code happens here, we don't care, because whatever single statement we don't care about, we know that this guy will give us n squared, right? And if you actually go a little bit crazier, well, not crazier, but if you would like to go to have fun, even with the patterns here, if you meet something like this or see something like this, so I equals to 0, I less than n, I plus plus, and another one, which is going to be 4, j equals to n, j is larger than 0, j minus minus, right? This will also execute for n squared. Okay. Again, let me just correct these stuff. So O of n squared, this is the polynomial order. O of n squared, this is also the polynomial order. Okay. So this is like, these are like the patterns which I actually wanted to emphasize on. So you guys, like when you see them, you immediately like can, you know, understand, aha, okay, where I can understand where this thing is going. Okay. Any questions so far regarding this bit?
No questions.
Okay, so if there are no questions and everything is clear so far, let's step up the difficulty just a little bit. And now this is going out a little bit of the, you will see a pattern, but it doesn't necessarily mean what you see. So this is very important that you focus before answering and take your time actually thinking about this. So I'm gonna have a for loop of I equals to 0 and I is less than n, I plus plus, come on. And another for loop for j equals to 0, j is less than I, j plus plus, and then code goes here, we don't care pretty much. But right now, we need to know what is the time complexity of this guy. Now this one, you cannot wing it, right? This is like the previous ones you could hack, right? So you hack, like you hack the exam. You say, aha, 2 nested for loops, it goes to n, it's fine. You can just simply plow through it and say, aha, okay, I can guess this, right? Without the need to look too much. But this one requires a little bit of thinking. And if you haven't noticed yet, the reason behind this is at least this guy, right? Because this condition affects how many times this guy will execute whatever code is in here, right? So what do we do in this case? That's a good question.
Is it factorial?
Nope. Nope, it isn't. Actually, surprisingly enough, I mean, well, I can actually like, how can I put this? It's actually convoluted a little bit. You will get to, you will actually get to n squared here, but it's convoluted why you got to n squared at the end. And if you are stuck sometimes, like in some cases, like what you see here, what you should do is you write it down. So you say, aha, okay, fine. Let us analyze this. So you say, okay, so if this is the code, which I'm trying to execute, whatever is in here, right? I have an I have J, I have my code, right? And then you say, okay, when I is 0 and J is 0, no execution. right? This code will never execute. So when I is equals to 0, you go down here, J0 less than I, it's not working, right? It's going to be false. So there is no execution. So the loop continues, right? So you draw a line, the loop continues. So you increment I by 1. J will be still 0, right? If J is less than I, which is true because I is right now bigger, right? Then this code will execute. So you get an execution. Okay? You start incrementing J, so you keep I still in there, right? Because this loop succeeded. So you actually increment J, so you say, aha, okay, J++. Now, J less than I fails because 1 less than 1, it is not true, so it will actually fail. So no exec, no execution, right? And then we draw a line, right? So right now, we back here. You increment the I, right? And then I will become 2. So J will become again 0, right? So there's an execution because you're starting over from here, isn't it? You are executing the for loop again. For every item, you execute this guy again, right? So there's an execution. And then for the second time, you increase J because it didn't fail yet. And then for the third time, you increase J. So there is an execution here. But then when you reach here, it will be no exec, no execution. Okay? Let's carry on one more time. You will actually go back. You will increment I to 3. Then you start J again, right? And because J is less than I, this code will start to execute again. So you get execution, right? You keep still the I because you didn't still fail this loop. You increment J, you get an execution again. So you execute that piece of code. You execute again that piece of code. Then you execute again, or actually, sorry, you don't execute again. So no exec when you reach the 3. Okay? And you stop, right? So at the end of the day, when you think about this, first the code will run once. Like, sorry, will not run at all. Then 1 time, then it will run 2 times, then it will run 3 times, right? If you look at it, and you can actually like, so if you look at it that way, first time, 0, nothing. Second time, it ran only once. So let me actually like highlight it right now. So, so here you go. First time, nothing. Second time, once. Third time, twice. Next, 3. Now you can imagine the next is going to be 4, and the next is going to be 5, and then 6, and then 7, right? It just keeps incrementing. So at the end of the day, your function execution is more like 1 plus 2 plus 3 plus 4 plus right? Plus n, right? When you think about this, because how it executes, you know, it executes once, then it adds up to twice, then it adds up to 3 times, and so on and so forth. The funny part is the sum of the natural numbers is equal to n times n plus 1 divided by 2, which if you expand this, it's going to be n squared plus n, which makes your polynomial order of n squared. It's a little bit convoluted, right? But you will never see this unless you just simply analyze what happened, right? So I just simply took the for loop and I just simply written the numbers. And I haven't done anything else. I just counted things. Knowing just this fact, you immediately know how to get this, right? Does this make any sense? People? Okay.
Yes.
Do you have any questions? Objections, or whatever you would like to call it? Okay. I will consider that everything is green and fun. Let's actually carry this on a little bit further. So I will not actually like, so this one required the trivia to know about. Well, not the trivia, like I think you guys studied this as well in schools, right? The sum of natural numbers, this is the formula of it. But let's actually have one more that is actually a little bit similar to it, right? So I'm gonna have here, let's say you have a p equals to 0 outside of a for loop. And then we have a for I equals to 1, p less than or equals to n, I plus plus, and then we have here p equals to p plus I. Right? I would actually like that you try this, if possible. So can you please just sit down? Like exactly, I'll give you exactly 10 minutes because you don't need more than 10 minutes. I actually expanded this while talking in, I don't know, like what, 10 minutes, I think, but I was talking to you. So this one, you need to figure out what is the time complexity of it. How do I know? This seems a little bit interdependent stuff, right? So the P is modified here, there's a check here. So what you say, okay, I'll put n equals to, let's say, 5 steps or 6 steps. It doesn't matter, right? So what you do is you analyze I. So you immediately say, okay, let's get down to the paper and pen or the whiteboard or blackboard. You say I here, here's P, here's my code execution. What is going to be the result of that code, right? And you carry on. So I actually like helped you out. So try to figure out what is I, what is P after code, and let's go with it. Okay, I will give you, there you go, 10 minutes just to figure it out. Honestly, I don't know if 10 minutes are up or something like that. Just let me confirm here. How's it going with you guys? Have anybody give it a try? Give it a thought?
I mean, I get the same answer as before, 1 plus 2 plus 3, this sum.
You're actually there. You're actually there. So you're right there actually at the ballpark. You actually on the right track. But I will actually like push it even a little bit further from there, because unlike the previous example, where we had the I and J are somehow tied together with an N, right? This one is not, but you are actually on the right track. So let's actually think about this. So if I actually equals to 1 and P equals to 0, okay, then when this code will execute, right, P is going to equals to 0 plus 1, right, which is going to equal to 1. And then the next execution, I will increment, right? And then P right now is 1, right? Because it's fetched here, because we said P equals to P plus I, right? So I will not actually draw it anymore because it will become super crowdy, but I will actually just simply like draw it only once to indicate this. Okay. And then at the end of the day, what you're going to end up with 0 plus 1, like the previous operation, which we had. I'm just writing it all down again. Plus 2 is going to equal to 3, right? And then you take that thing, you plug it in back, right? Which is going to be 3. This guy will increment 3, right? And then you're going to have the 0 plus 1 plus 2 plus 3, right? Which is going to equal to 6, right? And then you increment this again, increment I. There's going to be 6 because you plug in this guy back. And there's going to be 1 plus 2. I'm just ignoring the 0 right now. Plus 3, or let me be there, so just to be consistent. Plus 4, which is going to equal to 10. And right now, you really don't know exactly how long this will take because the jumping is actually kind of weird. You cannot actually predict it that very much. I mean, for now, when we are looking at this, you cannot eyeball it, you cannot guess it. But you know for sure that this is actually repeating for k times. And I'm going to call it k times because if you use actually P as an indexer, this whole thing, so this whole thing actually repeats k times, right? So at the end of the day, you have 1 plus 2 plus 3 plus plus k, right? Like in the previous example. If you use P as an indexer, you will never index in the same position. Like you cannot index in the position of the array like normally as you should do, right? Because you're not looping on every element or every second element. You are actually jumping in a very interesting pattern, right? So 1, 3, 6, and then I don't know, 10. Then I don't know what's going to be next. What? 14, 15, right? So you are just simply jumping in an interesting way. So what is going to be the complexity of this? Now, if you are actually having such a question, like similar to this in a test or an exam, or you meet it like, or you see it in real life, and you would like to, know whether this code will execute in a certain time. So you would ask yourself, oh, okay, what is the time complexity of this thing? So if we assume that the stopping condition of this thing, of this loop, if it wants to stop, it has to be at least it's going to equal or larger. So P has to be equal or larger than N, right? Sorry, larger than N, sorry. Now we have deduced that this P is actually, apparently, from what we see here, is the sum of the natural numbers, right? From this part, right there, which we said that it's going to sum up until k times, because n is something else, right? N is the n, the actual array, let's say, right? So we say we have a k, we made a variable called k, and we say it's going to actually repeat for k times. Now the sum of natural numbers, so we say p is going to equal to the sum of natural numbers, which is k times k plus 1 divided by 2, right? So if I actually substitute this guy with this guy, meaning that I will end up with k plus 1 divided by 2 larger than n, okay, which we can approximate it to k squared plus k divided by 2 larger than n, okay? And since we are interested in the polynomial order of a function, we can approximate this even further. We can say that this k squared is larger than n, right? Because we are interested in the polynomial order, we are not interested in the rest, okay? So we can approximate this again, and we can say, aha, okay, so if this is like this, then from the high school rules, we know that k is going to be larger than square root of n, right? So we can say that this code will have a polynomial order of square root of n, meaning it's written like so. Okay? And this is just because right now p is incrementing in a certain way that is almost independent from n. It repeats in a different way, right? How are we doing? Is this clear, guys? I mean, please, again, no need. I mean, if you are shy of the voice, just please write in the chat. How are we doing? Is everything is okay? Are there any questions?
Can you explain once more?
Yeah, sure. Okay, so let's go through this again. So I actually increment. Would you like to go from here, from where we started here?
For me, the last part is fine.
The last part is fine. Okay, so we said again that this, you already know what is this, why we got there, right? So we already said that 1 plus 2 plus 3 plus k, because of how the pattern of p is actually getting, right? The code execution, this code executes in that way. And the for loop actually is being dictated by these numbers. So we say that this code will repeat k times, where actually this k or this p, let's say, is going to be 1 plus 2 plus 3 plus k times, which is going to be the sum of the natural numbers. The sum of the natural numbers is this formula. And we said that the stopping, if we would like to know the analysis of this code, we need to know when it will stop, so we can understand how big, what is going to be the growth of this function, or what is the polynomial order of this function. So we said that if p will actually, like, this loop will stop when p is larger than n, because if p equals to n, the thing will still loop, it will still work. So if p larger than n, then we say, okay, what was p actually? What is the code? This p, what was the code? The code of p is this, right? 0 plus 1, and then the second loop, 0 plus 1 plus 2, and then the third loop, 0 plus 1 plus 2 plus 3, and so on and so forth. So we said, aha, okay, if p actually is the sum of the natural numbers, I'm just going to take out p, substitute it with this guy, right? and then I written it in a different form. So I said the stopping condition of P larger than N, I said the stopping condition is this guy. Okay. Now, since we are interested in the polynomial order, I said, okay, let us expand this and let's see what is the polynomial order of this function. And then we know that the polynomial order is the one with the highest exponent. So we immediately say, aha, okay, I can approximate this to k squared, right? This whole thing, I can approximate it just to k squared because I'm interested in the highest exponent or the variable with the highest exponent. And then this is just the high school math, or the primary school math, depending where you would like to go or where it was. So if you actually would like to eliminate this, you take the square root of the right-hand side of the equation. So we ended up with a function with a polynomial order of a square root of n. You could have actually also left it in this form if you want to, but it wouldn't be that useful. And since we are approximating things, trying to make things a little bit clearer to see, we just simply approximate it to this form. And again, this is the polynomial order of a function. Does this make any sense now? Is it better?
Yes, yes.
Okay. Okay, let's actually have one more example. And we can actually, like, after that example, we can stop right there. Okay, so because of the, like, I actually like took the difficulty a little bit up a little bit more. But hopefully you understand the how do you call this, the importance of trying things by hand. Like when you see something, you cannot hack it right away. Just try it by hand and see where it goes. Because sometimes things are a little bit different than what it seems. Let's say, and this is actually quite famous in algorithm, and you're going to see why in a minute. You have another example. So let me actually draw a line right there. And you have a for loop of I equals to 1. I is less than n. I equals to I times 2. And the code goes here, right? This is also interesting right now. This cannot be n. It's impossible for it to happen to be n, right? Does anybody know why?
It is getting multiplied by 2. It is not. It is not.
It's actually being.
I can't remember how the function is called. It's not.
It's called doubling.
Function.
Sorry.
It is a. It's not like the simplest straight line function. I mean, it is, but it's not.
It's not linear function. It is called. Huh? You're actually like you're there, but I don't know. Like I don't know if you're. Say, هذا لسه na bosanskom ako ti tešo.
Ne mogu da se sjetim na bosanskom.
Aha.
Znam na šta mislim, nego.
I know what you are thinking, by the way, but I was just like seeing, like, let me see if the guy just remembers it at least. All right. This function is actually logarithmic, right? Is that what you were thinking of, or something else? Probably something else.
Mislim, izgled. Mislio sam na izgled, sama funkcija nisam. To je logaritmska funkcija.
Aha. All right. All right. But okay, let's actually talk about the analysis. So let's actually analyze this thing. Okay. So at the beginning, I is going to equal to 1, right? So that's what's going to happen at the beginning, at least in the first loop. And then in the next loop, you're going to have 1 times 2, which is going to equal to 2, right? And then you're going to have 2 times 2 is going to equals to 4. And then you have 4 times 2 is going to equal to 8. And if you notice this is actually more like 2 of 0, 2 of 1, 2 of 2, 2 of 3, right? Like I'm just trying to let me divide this, right? So 2 to the power of 2 is 4, 2 to the power of 3 is 8, right? And then we can actually go on with this. So this is like the analysis of this guy. If you haven't noticed yet. So practically speaking, we don't know how far you can index in the array correctly, but we know it's going to actually repeat for 2 to the power of k times. So how much n is going to be, we don't care, but it's going to be like 2 to the power of k. It cannot be 2 to the power of n, right? So based on that, assuming that I is larger than or equals n is a stopping condition, and I is going to equal to 2 to the power of k, right? Because it's going to repeat 2 to the power of k times. We can say that 2 to the power of k is larger than or equals to n. We can simplify this, right? By saying, okay, fine, the stopping condition will be 2 to the power of k equals to n. If we simplify it, just simplify. Okay? Meaning that k equals to log base 2 n, making this function having a logarithmic order. So log base 2 n, and it is base 2. Not base 10 or any other bases, it's just always base 2. And in algorithms and data structures, we always look at logarithms by default. No, if nobody mentions this. In books, you will see it like this. Sorry. Log of n. People write it like so. And when they say log of n, it's always by default log base 2. Okay. So this is a default and this is what we know, at least in the books and everywhere else. When somebody talks about logarithms in algorithms and data structures, we always look at them as log base 2. Okay. So this is the this is an example of a logarithmic function. How are we doing? People, are we good?
Yes.
Yes, yes. Everything,
Hopefully your CPUs didn't fry yet.
everything is okay.
Sorry, I cannot hear you.
Everything is okay.
Okay. I think like I'm gonna actually like, because I probably stepped up the difficulty just a little bit faster, maybe. I will actually stop right here. And in the next class, I will review more patterns with you just regarding these logarithmic functions and other things like that. And we'll define with you what are the asymptotic notations. And then we can close that chapter. So hopefully, I hope that next time, I think next time will be the end of this complexity theory like kind of series, I would say. I think like looking at my notes here. Again, please understand that this needs practice. Go ahead on the internet, look at algorithms, look at them, like try to pick the easy ones without because branching we're going to discuss next time. So what happens if we have of like an algorithm which you like to analyze, which has a branching if else statements. While loops are going to be the same as for loops, so this is actually not going to be a problem for you, I think. Just pick up a random algorithm and see how you can actually, when you look at the code, how you can analyze it. You can actually even take one of your codes from your programming 1 homeworks, which you have done, or your exams from programming 1. Check out the source code which you had to write and see the algorithmic analysis of it. Can you analyze, for example, how many nested for loops did you have? What is the order of the function? This is actually going to be a good practice for you in the future. When you look at your code in the future, like when you are in production, you will immediately say, aha, okay, I know where to optimize. I can make, for example, make some things a little bit faster by scratching some functions or making some things like making less loops or something like that. Let me, I will stop recording right here.